I want to thank the organizers for their kind invitation. I'm really honored to be here to speak in memory of Professor Nambu. Unlike many of you, I did not have an extended connection with Professor Nambu. I've never worked at the University of Chicago, but actually I had some pretty memorable interactions with Professor Nambu because for one thing, he actually invited me to the very first string seminar that I gave. I was still a graduate student in Princeton, and I was sitting in my office one day. I get a phone call from Nambu inviting me to give a seminar, and this was right around 30 years ago. So I came here, I think in May '86, and I had a bit of a problem with my flight. And he actually got very worried, started looking for me. He was really an incredibly gracious host. I remember how he even took me out to dinner. So this was just to show how incredibly nice a person he was. And of course, in terms of his scientific impact, he's truly one of my heroes. Now, this paper came up a lot in, oops. What did I do? Yeah, this paper. A model of a unified model of pions and nucleons that appeared due to Nambu and Iona Lasinia. It had this famous Four-Fermion. How do you? Okay. Yeah. So it has this famous Four-Fermion interaction, which can also be written as psi bar left, psi right times complex conjugate. So it's nicely arranged to have an extra U1 chiral symmetry. And then, of course, the point was that this chiral symmetry can be spontaneously broken via condensation of a fermion antifermion bilinear operator. And this was basically the first example of dynamical symmetry breaking in a relativistic system. And in this talk, I will kind of discuss variations on this theme. In particular, now in the modern language, we have various extra knobs to dial, namely dimensionality of the space-time D and also the number of fermion components N. And we will see how sometimes as you reduce the number n, you can arrive at the situation when a conformal field theory gives way to a Nambu-Goldstone phase, which is just another conformal field theory, but this time free. And let me start by considering the closely related Gross-Neveu model, which does not have this gamma-5 interaction. Since we want to continue in dimension, gamma-5 may be scary, but I will argue that it's actually not that scary. But the motivation for the GN model was actually to study it initially in dimension 2, where it becomes renormalizable. So of course, in the NJL paper, they had this non-renormalizable quartic interaction, and then they treated it with some explicit cutoff. But then if you're in 2 dimensions, you can do a better job. However, we will primarily be interested in going above the 2 dimensions, and then you have to play a certain game, which I'll describe. Then there is another way to write the Nambu-Iona Lasinia interaction using the extra gamma mu. And then the first term is just the Turing model, right? So we will also discuss another interesting dynamical model, which is the Turing model, and that turns out to be related to QED. So the UV fixed point, this is a little more complicated, but at least for large n, the UV fixed point of the Turing model has a kind of UV completion, which is just a QED theory. And the way you see it is from the point of view of the Turing model, you have a kind of emergent gauge field, but in QED, it's just present automatically. And both of them at the fixed point have exactly the same induced effective action, which is non-local, because it's just, the quadratic term is just given by the 2-point function of this current operator. Okay, so let me talk a bit about the Gross-Neveu model. The initial excitement about it was that in 2 dimensions it has some similarities with 4D QCD, namely it is asymptotically free and exhibits dynamical mass generation. And there is another 2D model which one can compare with similar physics, which is the ON nonlinear sigma model. And both of these, if you go into dimensions slightly above 2, both of these have weakly coupled UV fixed points. And then the question is, so since UV fixed points are not entirely satisfactory, what is the completion of them? How do you think of these theories equivalently as flow in the usual direction from UV to IR? Now, the answer for the ON nonlinear sigma model is completely well known. It's just a linear sigma model. The Wilson-Fisher linear sigma model. But I'll talk about also the answer for the Gross-Neveu model, which is perhaps not as well known, but it actually has been in the literature for years. So let me first just remind you how this 2 plus epsilon expansion works. So the beta function, there is this asymptotically free minus sign here, and then further corrections, and then because of explicit dimensionality of G in 2 plus epsilon, you also have this term. And then at the fixed point, G star has this standard epsilon expansion. And then you can develop the 2 plus epsilon expansion of various operators and so on. And then there is a similar story in ON nonlinear sigma model developed by Brezanens and Justin. But here it's a little more complicated because with scalars there tend to be infrared divergences, but for fermions everything is very clean and there are no IR divergences. Now you go to, then you venture higher in dimensions, and then for the ON sigma model, we of course know what the upper critical dimension is. It's 4, and then 4 minus epsilon is just described by the 5-4 theory, which now has a weakly coupled IR fixed point. So you can develop then 4 minus epsilon expansion, and then you can kind of marry the two, and using these 2 epsilon expansions actually construct pretty reliable estimates of Pade in the entire range between 2 and 4 dimensions. And this is a great practical tool for CFTs in D equals 3 for the 3D Ising model, O2 model, and so on, which all have physical applications. Okay, so the hope is to construct similar things for these Four-Fermion theories, construct a similar approach. Okay, and so here comes the UV completion, so the Gross-Neveu model also is believed to have upper critical dimension 4, and its UV completion is just a multi-flavor Yukawa model. And we'll see in a second why this is, but basically, there is an extra scalar field that you need to add, and then this extra scalar field couples with the Yukawa interaction to the fermions, and then you also have to add the other marginal operator, sigma to the 4. And this, as expected, has an IR fixed point in 4 minus epsilon. And then using these 2 epsilon expansion, we can then study this Four-Fermion CFT in the entire range between 2 and 4 dimensions. So it's a completely parallel story, but it's even simpler in the case of the Four-Fermion theory. Now, for tiering model, completely similar story. You can then study QEDD in 4 minus epsilon dimension. This is, again, a theory which is infrared-free in 4 dimensions. So one finds, so if you write down just the standard QED beta function, you have to add this minus epsilon over 2e term, and you find a weakly coupled fixed point in 4 minus epsilon dimension. And this is believed to be the continuation of the tiering model up to near 4 dimensions. So that's another glorious Four-Fermion model kind of solved. So one of the reasons there has been renewed interest in these theories is that when n is large, all these conformal models actually have higher spin currents which have small anomalous dimensions. So And in general, we're wondering, whenever we have a CFT, we have to wonder what is the ADS dual of the CFT. And in this case, the ADS dual is somewhat unconventional because in addition to the massless graviton, it also has massless higher spin fields, which are dual to these approximately conserved currents. And there is this whole story about this, which I will not describe in detail, but there is a very simple connection between, you can, for example, just consider the theory, say, of n free fermions, or you can consider the same theory with the psi bar psi squared interaction. It turns out that the two are related very simply in ADS, that one just has to modify the boundary condition for just a single scalar field that's dual to psi bar psi, and this was initially described in this paper that Polyakov and I wrote. So it's a kind of tested strategy for a lot of this ADS-CFT duality. Okay, so this brings us to the necessity of developing the 1/n expansion for these models, because once we have this 1/n expansion, it all falls into place, and we can then compare with these epsilon expansions, compare with ADS description, and so on. So if you look, for example, at the Gross-Neveu and scalar ON models, they have very similar structure. They both have double trace interactions, namely a square of a singlet operator, and one can rewrite this square using this extra sigma field, the auxiliary Hubbard-Stratonovich field, which couples in this way. And then, so you can say that this field is a kind of has induced dynamics because its kinetic term is non-local and it comes just from this two-point function of operator O. So you can say that the dynamics brings in this additional scalar field, and since this two-point function is of order n, this allows you to obtain 1/n corrections in a very simple, elegant way, and actually in continuous dimension. So it's not just true in one fixed dimension, it's true in continuous dimension. This is the non-local term. And you see that this sigma is really the same sigma that we found in this Gross-Neveu-Yukawa model. So this sigma basically becomes a local field of dimension 1 in 4 minus epsilon dimensions, and it becomes literally this field. So it actually acquires a local kinetic term only in this 4 minus epsilon dimensions. So one thing that one can check rather explicitly how this weakly coupled epsilon expansion actually matches on to this large n story here. Okay, so and then at the critical point, you just drop this sigma squared term. Everything is given by power law correlators. And this game was played very extensively in the 80s and 90s. For example, Gracie developed for the Gross-Neveu model the picture of 1/n corrections. And these 1/n corrections are computable as a function of D. And then so this is a little bit sophisticated. It's a kind of resummation. And then you can compare these results with just the standard renormalized perturbation theory in either 4 minus epsilon or 2 plus epsilon, except you use two different models, right? There are two different renormalizable models. One is psi bar psi squared, and the other one is the Yukawa model, and this perfectly agrees. So this is one way to test all this large n approach. Okay, so what about Nambu-Ioannolesino CFT? It's maybe you haven't heard about this one, but I think it's there. It's so there is only this extra gamma 5 interaction, but we shouldn't be scared of it because, for example, this also appears in just the West-Zumino model, and there is a pretty standard way to treat it. So the difference is that it has an extra U1 symmetry, extra chiral U1 symmetry compared to the Gross-Neveu model. And actually, Gracie already in '93 computed the fermion anomalous dimension in this type of CFT. It's similar. Basically, you have two Hubbard-Stratonovich auxiliary fields. One is sigma, and the other one is a pseudoscalar pi. And basically, you find these completely explicit answers. And I don't know if this has been fully worked out, but now actually we're thinking about playing a similar game of 4 minus epsilon dimensions for this non-Boolean CFT. And we expect that the conformal field theory will exist actually for the entire range of dimensions, even for the smallest number of colors. So if Nambu and Jona Lesinia decided not to look directly in 4 dimensions, but if they ventured in 4 minus epsilon dimensions, they would just find the CFT. So that's kind of fun. So CFT is a pretty generic behavior of these models, not just for large n, but even for other small n. So now let me talk a bit about some specific calculations that we recently did. Well, there are some, in addition to scaling dimensions, there are these rather interesting quantities Cj and Ct, which I think Subir indirectly alluded to them in his talk. They're related to universal conductivities in a CFT. And Ct in particular enters in many contexts. It's also very useful for shape dependence of entanglement entropy. And it's also, of course, a measure of degrees of freedom. For example, in D equal 2, it's just the C of the homologic of C theorem. But once you go above 2 dimensions, it's no longer an anomaly. It's still an invariantly defined normalization of the TT 2-point function. There is no freedom in changing normalization of T mu nu because it's fixed by the word identity. So how do you, suppose you want to compute these quantities. Turns out it's a little harder, but still quite doable. So in large n theories, you always have this type of large n expansion with these extra coefficient Cj1 and Ct1. And you can use the graphical rules, again, attaching these induced propagators of the sigma field to obtain completely explicit d-dimensional answers. So for Cj, it's not that difficult, and one obtains these results. You see this remarkable universality that this eta1 is the leading anomalous dimension of the fermion field, and this is the leading anomalous dimension of the scalar field. You see that it's completely universal. And Ct1 is more complicated. You have, in addition to these diagrams, there are also diagrams with 2 triangles, which I think in condensed matter literature are known as Aslamazov-Larkin diagrams. And they caused us a lot of pain. It introduces a host of other complications, which I will not go into, but my collaborators persevered and pushed through these calculations. And then the result turned out to be this for the GN model. And the one reason we knew that this is probably a correct answer is the test versus 2 plus epsilon and 4 minus epsilon dimension. In fact, we were missing some ingredients, and for a year they were not agreeing. So this is kind of seems like a pretty safe strategy, but still I would not bet my head on this formula. Now, for the ON model, actually an answer was available much earlier due to Petko, and in the course of he used a different technique which was based on OPE, a known 4-point function of scalar fields. And in the course of reproducing his answer diagrammatically, we basically learned how to do things correctly. So you see that for this quantity, it's not as universal. Like there is some similarity, but this rational factor is not the same for the ON model as for the GN model. There is a different d-dependence here. It's similar, but there is a somewhat different d-dependence. Okay, so now what about if you go to the physically interesting case of 3 dimensions, you see that, for example, for the Four-Fermion model, the correction, the 1/n correction is actually much smaller compared to the ON model. As I mentioned, Cj is universal. This is electrical conductivity, and Ct, I guess, is the thermal conductivity coefficient. So these results could potentially be, if one finds a condensed matter system which is described by the Gross-Neveu model, maybe this will be comparable with the data. But there is also a theoretical motivation, which is to test this putative RG inequality. Is it really true that CT in the UV is bigger than CT in the IR? And this was one of our theoretical motivations. So the fact that in 2 dimensions, this is definitely true, as proven by Zamolodchikov, you would expect that when you go to 2 plus epsilon, it's not too far, right? So it should be okay. But our big surprise was that it actually, right above 2, it's violated. It's violated between 2 and about 2.3, but then it becomes good. It becomes good, and in 3 dimensions, it just happens to work. So we were actually, there is one known supersymmetric counterexample to this inequality in 3 dimensions, and when we embarked on this, we thought we would find more, some non-SUSY counterexamples, but we haven't found any, actually. All these examples do obey this inequality. Okay, so now similar calculations in conformal QED, which, as I mentioned, is also like, in some sense, a Four-Fermion model. It's a multi-flavor tiering model where this photon can be thought of as emergent. This is somewhat harder technically, but the strategy is similar. Again, you have this extra lines that you have to attach, except now they're gauge field lines. And here you get these more, things start looking more transcendental even for CJ1. There are these derivatives of psi functions appearing. But again, there is a mass anomalous dimension that multiplies this whole leading correction. And again, the 4 minus epsilon dimension expansion for QED is a great tool to compare and make sure that it actually works. So now that's the real mess. Actually, the diagrams were set up by Ha and Strack. And now, basically, the complexity is that the T has 2 pieces. One is just from free psi, and the other one from A psi bar psi. So there are many more diagrams and more opportunities to screw up. But, but basically, we struggled a lot with this, and with an analytic regulator, we find the following answer, which matches the 4 minus epsilon expansion very nicely, as far as we can tell. And also, it does obey the CT-UV bigger than CT-IR also in this example. So this I already said. And another test is when you go to the D equal 2 case, then we know the exact solution. It's just a multi-flavor Schwinger model. And this we know the exact central charge, so we know the size of this 2 over n correction. And now our technique allows us to plot it as a function of D. And you see that the smallness of the correction in D equals 3 is because it actually crosses from something pretty large and positive to something negative. So there is a lot of room between 8 and minus 2. And so if you want a quantitative answer, actually large n seems to be the way to go. And these are the explicit answers that we find in D equals 3, which again, I mean, it could even be potentially comparable with some experimental data, I hope. Okay, so now I guess I have another half an hour, or yeah. So the C is one. Let's just remember how things work in 4 dimensions, right? In 4 dimensions, there are 2 conformal anomaly coefficients. One is C, which is sort of bad, and the other one is A, which is sort of good, right? And A, because we know for A there is an A theorem, which has been proven by Komargotsky and Schwimmer, and that definitely obeys this AUV bigger than AIR. But so C, it's hard to know, right? It starts out good in 2 dimensions, but by the time you reach 4 dimensions, it's bad. as we saw, still in 3 dimensions, it mostly seems to work. So it's still a pretty useful measure of the number of degrees of freedom. So now let me talk about the A-type quantity, which can be obtained from the sphere free energy. So there is a sort of emergent law that if you, in any dimension, there may be some theorem which is based just on the free energy on the sphere. So the idea is take the Euclidean CFT, map it to the round sphere, and calculate the determinant log z sd, and see what this gives. Now, in odd dimension, for example, in d equals 3, this gives something that we call the F theorem. The basic F theorem is just a positive quantity, which I'll show in a second what it means. But in 4 minus epsilon dimension, this has a pole, right, due to the anomaly. Essentially, in 4 dimensions, you have an anomaly, and it manifests as a pole. So to cancel this pole, Giambi and I decided to multiply by sine pi d over 2. It actually was sort of staring in our face. If you compute determinant as a function of d, there is always sine pi d over 2 in the denominator. So we just canceled it. And then you obtain what looks like a perfectly nice monotonic function, which smoothly interpolates between A anomaly coefficients in even and F values in odd dimension. And this is not a pure curiosity. It turns out that this sphere partition function also gives the universal term in the entanglement entropy in actual Minkowskian theory. For example, in 2 plus 1 dimensional theory, it gives the universal term of the circle entanglement entropy. So it's a useful and somewhat physical quantity. So now let's just explore this quantity. And for example, for free conformal scalar and fermion theories, it's possible to derive this formula for these F tilde coefficients. Here are the integral representations. I won't tell you how I got them, but they definitely work. In all integer dimensions, they give the right anomaly. It's actually a very useful tool. Like, if you want to know the A anomaly in 136 dimensions, I think you can just compute this, and it will work. Yeah, I mean, usually most papers just give you 2, 4, 6, 8, 10, and then they stop. But this works in all dimensions. And moreover, this F tilde is completely monotonic, positive. And this is already good news, because when you gap out this theory by adding a mass term, if you want this quantity to be monotonic, it's just going to drop to 0. So if this became negative, this would immediately violate this F theorem, the monotonicity theorem. Okay, so this is just the boring free conformal field theories. What about interacting ones? Yeah, and our hope is that this F tilde UV is bigger than F tilde IR, not just in integer dimensions, but also in continuous dimensions. And we've tested a whole bunch of examples, like large N examples, epsilon expansion examples, and so far we haven't found any problem, any counterexample. They always appear to work in unitary examples. So just to show you how hard some people at Princeton work, this is for ON model to some insanely high order. You get up to epsilon to the 5th order. This actually is insanely hard work, because in addition to computing these diagrams, you need the curvature counter terms. It would take a whole separate lecture to describe, because unless you add curvature counter terms, you will not cancel the log R dependencies. And when the theory is conformal, all the R dependence on the sphere has to cancel. So there is a whole story with curvature terms that's painful, but we believe we have it under control. And then you do Pade approximation, and out pops this amazing result, which is, suppose you want to know the entanglement entropy for the 3D Ising model, 2 plus 1 dimensional Ising model across a circle. I'm not sure you want to know it, but here we can give you the answer, because on one hand, we know F tilde in this epsilon expansion near 4 dimensions, and you also know the exact answer in 2 dimensions. because it's just C equal to 1/2. So you construct this plot, and it really dips from near 1. This is F over F3 to exactly 1/2. And then you check what is it doing in 3 dimensions, and it's still amazingly close to 1. You find that F3D Ising to F of the free field is only 2% off. So it obeys the F theorem, but F theorem just tells you this has to be smaller than 1, but this happens to be extremely close to 1. And this seems to be an emerging pattern for a lot of quantities in these conformal field theories, that even at small n, there is a sector which is very close to free field. For example, from conformal bootstrap, they obtained CT of 3D Ising to CT of 3D free scalar, and it was only 5% off. And just to go to something even more familiar, we know that the dimension of phi in 3D Ising model is only 3.6%. This is known since the times of Wilson and Fisher. So it's not that surprising, but still the sphere is it seems even closer to the free field. And as I told you, this is also the entanglement entropy of the disk in this model. Now, same game for Gros-Neveu. It's still, we haven't written it up, but here things are even better because there is no infrared divergences near 2 dimensions, so you can do clean 2 plus epsilon and 4 minus epsilon, kind of marry them together, construct good approximants, and you see that, so here are the plots, again, of F to F3, and you see that, again, this always goes, so this is the comparison with the theory of the free fermions, and this is theory of the free fermion plus a scalar, kind of Gros-Neveu-Yukawa type model. And here it's always below 1, here it's always above 1. So F tilde UV is always bigger than F tilde IR. So all this evidence points to the usefulness of this thing. So now let's try to apply it to something where we don't quite know the answer, which is, so one of the things, so the original picture of Nambu and Iona Lasinia was this development of a condensate, right? Symmetry breaking via dynamical development of a condensate. And something like this is believed to happen in 3-dimensional QED. But it's believed to happen as a function of the number of flavors, right? If you start with a huge number of fermions, then the theory is certainly in the conformal phase. It's just a fairly weakly interacting conformal theory of all this soup of fermions. But then there is this appealing picture of what can happen when an F is small, which is the breaking of something that's sometimes called a chiral symmetry, although it's discrete. Essentially, the picture is like this. You start with an F 4-component spinors, and this is how Appelquist and Pisarsky originally wrote, because they were really thinking of it as a dimensional reduction of the 4D gauge theory in a thermal setting. And this notation is often used. So one cautionary note, when you read the paper on this, first make sure what an F refers to. Is this the number of 4-component spinors or the number of 2-component spinors? I think there is some division between camps on this one, but I'll use the NF as 4-component spinors. Then when you go to 3 dimensions, there is automatically 2NF 2-component spinors, which we call chi1 and chi2, and this automatically avoids the parity anomaly. So the parity anomaly is avoided here, and the model has SU2NF global symmetry just in 3D, because somehow these spinors are sort of on equal footing. So there is this enhancement from SUNF here to SU2NF in 3 dimensions. But the mass term, which is parity invariant, which is written in terms of these fields like this, actually explicitly breaks SU2NF symmetry down to SUNF cross UNF cross U1. So it's kind of forbidden by the symmetries of the UV theory, which is this QED. But there could be a dynamical generation of a condensate of this operator. And still the big question is, when and if this happens. I think there is some lore that is being now challenged now by a new round of lattice experiments. Before I plunge into this, let me just also exhibit the computation of this sphere free energy in the large NF expansion. Now you actually obtain the leading NF term is just from free fermions, but now there is a log correction. Actually, the gauge field brings in this log correction. And even though this grows without bound, it does not violate the F theorem because the UV Maxwell theory, which is decoupled, is not conformal in 3 dimensions, and it has a, strictly speaking, divergent value of F. So this will come in handy also for... I'll make a comment actually at the very end about this formula. But so the picture that I think Pisarsky originally invented was that the condensate of this operator will appear. It preserves parity because it's an assumption. We want to keep the parity theory parity invariant. So you see that there is each of these flips sign under parity, but you just interchange the two, so there is a definition of parity. But obviously, this breaks SU2NF to this subgroup. And then there are the Nambu-Goldstone bosons. There is some 2NF squared Nambu-Goldstone bosons. And then you can try to use the F theorem or some other new inequalities or old inequalities to try to constrain this. So one very basic picture, actually, that has emerged in the literature is that what's causing this condensation? That for large n, there is simply no relevant operator that preserves the symmetries. Namely, this operator is certainly relevant, but it does not preserve, we cannot add it in the Lagrangian because it breaks the symmetry. So what will happen is just that only this operator squared can be induced. And this operator, you have to know whether it's relevant or not. So the picture is that this quartic fermion operator can cross over from irrelevant to relevant at some n critical and cause destabilization of CFT towards something that Nambu and Ioannolesini envisioned. It's very hard to know because it's hard to compute the dimension of this operator. You can do 1 over NF expansion, but it turns out that the leading 1 over NF correction is too wimpy to do this. If you just use that correction, you will not see any condensation. So actually, Tarun Grover was the first one to try to constrain it using the F theorem. And since we started computing things to some insanely high orders in epsilon expansion, we repeated his exercise. But now we did all this. There is again this logarithmic term. And the test of this is again, so now this is the F tilde as a function of dimension. This is the sphere free energy as a function of dimension. And then we can try to do dimensional continuation and estimate what happens in 3D. And the surprise was that the large NF expansion was extremely good even for pretty small NF. So this is the result of all this epsilon expansion extrapolation, and this is just so this is the Pade formula, and this is large n, and they're very, very slightly different. So now you can just apply this idea of F theorem to constrain n critical. And you get a pretty concrete result. You get the result that already for NF equal to 5, the theory is guaranteed to be in the conformal phase. No doubts about it. So for NF 5 and higher, basically there are too many Nambu-Goldstone bosons, right? Because their number grows quadratically with NF, and the UV theory has just the CFT grows linearly with NF. So,
4 components for fermions.
Yeah, this is 4 components. Yeah, by NF we always mean 4. So for you it would be 10, which is, yeah, it's still not an incredibly stringent bound, but it's good. It's a good feeling to know something completely solid, I would say. Okay, so So now let me try to tell you something a bit more risky, but maybe a better bound. And this is what we learned as a result of all this hard work on CT, which is, so here is a question mark because it's not rigorous, but suppose we do apply CT UV bigger than CT IR inequality for this flow. And then you don't even need to calculate anything practically because the UV, it's a lot like this Appelquist et al. Bound, but instead of thermal free energy, we just use the CT. Now, the UV theory, as I mentioned, is not conformal, but you can still define CT for it just by using the light cone component. This is like T++. So we have a vector which is null. We multiply T mu nu by two of these null vectors, and this gives you a completely well-defined Maxwell contribution, which is 9/32 pi squared. And this is the contribution of free fermions. And now in the symmetry broken phase with Nambu-Goldstone bosons, we get this number, which is quadratic. You equate the two, and you find n critical, which is 1 plus √2, without basically almost no calculation, no epsilons, no. And also you get a much more stringent bound. So now you say that if this is true, then it shows that for NF being 3 and higher, the theory is conformal, and the only question mark is about 1 and 2. Name for you, it's 2 and 4, right? Okay, so now the lore, Kogat and collaborators did the simulation for what we call NF equal 1 and appeared to convincingly see a condensate. But now there is a new round of lattice work by Narayanan and collaborators, and they appear to be challenging this. So I think it's actually a good time to revisit all this. This proves when condensation cannot happen. It does not prove that it must happen. Okay, so that's so I think it's what happens for low NF is actually very interesting. And now, just as a comment about Son's talk, so Son was talking about, in our description, NF equal to 1/2, namely just a single doublet. And based on what I know from the 1/n expansion, so that theory, you can cancel the parity anomaly by simply saying it's a charge 2 fermion, a single charge 2 fermion. But it's extremely hard to study that theory because, first of all, 4 minus epsilon expansion is no longer available. There are just too few species. 2 plus epsilon is never available in the tiering model. So you only have 1/n. Based on what I see in 1/n, I think this could well be an example where psi bar psi time reversal breaking dynamically happen. Namely, you develop psi bar psi condensate, and this theory just has a gapped state. Now, but our condensed matter friends tell us, no, this theory may be dual to a free massless Dirac fermion. I think these are the two possibilities, and it would be really hard to prove which one of them is correct. Based on large n, I see that it's already on the side where this psi bar psi squared operator is relevant. Yeah.
Is it clear that it's not an interactive CFT?
Well, there is no. I think the CFT may be destabilized, namely that this psi bar psi squared operator that preserves all the symmetries of the problem, if it's relevant, it just could destabilize this CFT. And at least that's the argument for where the uncritical happen. So I'm sort of suggesting that an F equal 1/2 may be already on the other side of uncritical. But who knows? I mean, it's the kind of hard dynamical question that.
It may be destabilized, it doesn't mean it will break the symmetry. It will still flow to some other.
Yeah, I think if it does flow, I think my guess would be that it just develops a psi bar psi condensate, and then there is some kind of U1 level 2 topological description of it. But who knows? I mean, as we know, there are interesting papers appearing on how this could be just described by how this could be a CFT, and it's just a free CFT. So would be good to know which one it is. Okay, so now just a final comment. So I've been talking about extrapolating between 2 and 4 dimensions, but some of the work we've been doing is going above 4 dimensions. And then this whole picture with this Hubbard-Stratonovich field actually is valid even high above 4 dimensions. For example, you can push ON model to 6 minus epsilon dimension, and you get this renormalizable field theory, which we checked works to all orders in 1 over n. And if you say, what about 8 minus epsilon? No problem. All you do is you just, instead of d mu sigma squared, you add box sigma squared. And so on and so forth. So all these models have some kind of life, even in arbitrarily high dimensions, if you only worry about 1 over n expansion. They're non-unitary theories, but for the purposes of Euclidean statistical mechanics, they may have some interesting applications. So this continuation in dimension even works when you go high above 4 dimensions. Okay, so now let me conclude. So for me, it's been a bit of I wouldn't call it sentimental journey, because until 2 years ago, I never worked on epsilon expansion. So it's fun to learn some of the great stuff that was being done, starting with the Nambuya and Alesina work and this amazing wave of results in the 70s, which allow you to study these physically relevant CFTs to a very good approximation. And now there's another reason to work on this, is that there is all this conformal bootstrap, which sometimes buys you very precise numerical results. But I think these 1 over n expansions are providing good checks and balances for the numerical results. Sometimes there are disagreements to be ironed out, and so it's really a good interplay between the two, kind of resurgence of a lot of basic field theory. And a more theoretical reason to be interested in them is these RG inequalities, gaining some intuition, testing them, what makes sense, what does not make sense. And more specifically, this Nambuya-Alesina CFT, with the exception of just a few papers, it's not very well explored. It does have extra symmetry, say, compared to Gros-Neveu. It has an extra U1 symmetry, and would be really fun to actually find out what it does, how it's different from other Four-Fermion CFTs. And we are actively thinking about this. And now, just a few comments. So I started the talk about with a picture of Nambu. I think it was right around the time I met him 30 years ago, and now you'll see something familiar. That's actually the last time I saw Nambu was this appeared prominently in Nati's talk also. Was this wonderful 60th birthday symposium for Toru Eguchi, and was a very fun event, and this is a great picture to have. And then, actually, that fall, during the Nobel Prize predictions, I have witnesses. I totally out of the blue said that Nambu, this may be the year he actually gets the prize, totally uninformed. And then the next day, it turned out to be true, so I was very excited. I sent him an email, and amazingly enough, he responded. He responded in his characteristic, super polite way, pretty short time after, and he sent this slide. This is actually something he made. And I think we will really miss him, and it's a great way to say thank you to Nambu for all he's done for theoretical physics. Okay, thank you.